All right, we're now at section 17.4, resistance and Ohm's law. Let's move this off to the side and let's take a look at the figure. When a voltage, that is a potential difference, delta V, is applied across the ends of a metallic conductor, the current in the conductor is found to be proportional to the applied voltage. If the proportionality holds, we can write this relationship. Delta V equals IR. Here, the proportionality constant R is called the resistance of the conductor. In fact, we define resistance as the ratio of the voltage across the conductor to the current it carries. R is defined as delta V over R, and the units of resistance is volts over amps, but we call it ohms. That's the capital letter omega. The resistance is in ohms. Here the proportionality constant R is called the resistance of the conductor. In fact, we define the resistance as the ratio of the voltage across the conductor to the current it carries. And I probably already said that, but it bears repeating. If a potential difference of 1 volt across a conductor produces a current of 1 amp, the resistance of the conductor is 1 ohm. If an electrical appliance connected to for example, if an electrical appliance connected to a 120 volt source carries a current of 6 amps, its resistance is 20 ohms. Okay. We can compare the concepts of electric current, voltage, and resistance to the flow of water in a river. As water flows downhill in a river of constant width and depth, the flow rate, or the water current, depends on the steepness of descent of the river and the effects of rocks, the riverbank, and other obstructions. The voltage difference is analogous to the steepness and the resistance to the obstructions. Based on this analogy, it seems reasonable that increasing the voltage applied to a circuit should increase the current in the circuit, just as increasing the steepness of descent increases the water current. Also, increasing the obstructions in the river's path will reduce the water current, just as increasing the resistance in a circuit will lower the electric current. Resistance in a circuit is caused by collisions between the electrons carrying the current with fixed atoms inside the conductor. These collisions inhibit the movement of charges in a similar way that friction retards motion. For many materials, including most metals, experiments show that the resistance remains constant over a wide range of applied voltages or currents. This statement is known as Ohm's Law, after George Simon Ohm, who lived from 1789 to 1854. He was the first to conduct a systematic study of electrical resistance. In Ohm's law, we understand R to be independent of delta V, the potential drop across the resistor, and I, the current in the resistor. A resistor is a conductor that provides, A resistor is a conductor that provides a specified resistance in an electric circuit. The symbol for resistor in circuit diagrams is a zigzag line shown in the figure above the picture. The bottom photo is an assortment of different types of resistors. You can see the ones that are little circles with dials on them. Those are variable resistors. As you can turn them and it adds more wire, which adds more resistance. You can also see there's some in the center left. Those have sliders too. We'll see some of those in some experiments that we perform. Okay, Ohm's law is an empirical relationship and is only valid for certain materials. Materials that obey Ohm's law, which means that they have a constant resistance over a wide range of voltages, are said to be ohmic. Materials having resistance that changes with voltage or current are non-ohmic. Ohmic materials have a linear current-voltage relationship over a large range of applied voltages, as illustrated in the figure on the left. Non-ohmic materials have a nonlinear current-voltage relationship, as you can see in the figure on the right. One common semiconducting device that is non-ohmic is a diode, a current element that acts like a one-way valve for current. Its resistance is small for currents in one direction, positive delta V, and large for currents in the reverse direction, negative delta V. Okay. As we've already seen, electrons don't move in straight line paths through a conductor. Instead, they undergo repeated collisions with the metal atoms. Let's consider a conductor with a voltage applied across its end. An electron gains speed as the electric force associated with the internal electric field accelerates it, which gives it a velocity in the direction opposite that of the electric field. A collision with an atom randomizes the electron's velocity, reducing it in the direction opposite the field. The process then repeats itself. You can think of this as analogous to an internal frictional force. This is the source of a material's resistance. The resistance of an ohmic conductor increases with length, which makes sense because the electrons going through it must undergo more collisions than a longer conductor. A smaller cross-sectional area also increases the resistance of a conductor, just like a smaller pipe slows the fluid moving through it. The resistance is proportional to the conductor's length and inversely proportional to its cross-sectional area A. There you go. Resistance is equal to rho L over A. Where the constant of proportionality rho is called the resistivity of the material. Every material has a characteristic resistivity that depends on its electronic structure and on temperature. As you can see in the table, sorry about that, good electric conductors have very low resistivities, and good insulators have very high resistivities. Because resistance values are in ohms, resistivity values must be in ohm meters. That ends this section on resistance and Ohm's law. Next, we'll discuss section 17.5, which is the temperature variation of resistance. Right now, we covered the resistivity. That's the column highlighted in blue. Next, we'll talk about the temperature coefficient of resistivity. That's the column not highlighted, but we'll get that to in the next section.